On a server with low users and low traffic, the server should be able to handle the load without any issues. However, when it suddenly receives a huge amount of traffic, the server will not be able to keep up anymore and fail. One thing you can do to solve this issue is by upgrading its CPU and RAM. This is called vertical scaling, and you can only upgrade so much. What most systems do is to add more servers and use what's called load balancers to distribute traffic across the servers. Today we will be building one to understand how they work. Load balancers, at a high level, are programs that accepts incoming connections and distribute it on different servers, based on a set of algorithms you can choose. These algorithms can be how you want, but one of the most common algorithm for this, and the one we will be using, is called least connections. Just like the name suggests, it's an algorithm that figures out which server has the least traffic on it, and redirect the traffic there. Before we can get started, let's just take a look at key components our load balancer will have. We need to receive incoming connections, have a way to know which server has the least traffic on it, and a way to redirect traffic into it. We will be also using Rust for this project, but I hope it's not going to be an issue understanding the concepts. We will be just starting simple by accepting TCP connections and replying into it. Here we will be creating a listener that binds to localhost port 4321. Then just displaying in the terminal that the load balancer is running. Next we will be accepting incoming connection. The stream here is actually a result type, so we would need to extract the OK variant. Now we can write into the stream to reply. We will open up two terminals, one running the load balancer and the other one for using netcat to test it out. Next we will be redirecting the connection to another server. We will create a function called balance that accepts the client stream. Then, for now, we will connect to a single server that this connection will redirect to. How the redirection will work is, we will continuously read the bytes from the client stream and write it into the backend. So we will make a loop and a buffer where we will store our request, then doing a pattern match on a read function in our client stream. This function will return a result with the number of bytes read. If it's OK and the number of bytes read is 0, this usually means that the client is done sending data or the connection has been closed. If this is the case, we just break out of the loop. Next is, we just extract the OK variant with the bytes read on it. Inside, we just call the backend stream writeAll function and pass in the request buffer. And in the case where the read function returns an error variant, we just ignore it, just like I ignore your mom's calls when she is calling me at night. Since we have no server created yet, we will be using netcat to create dummy server for now. We can do this by doing nc-l127001-p9001, just like the address we put in our code. If we now go to this terminal and use netcat again to connect to our load balancer, which is on port 4321, and type stuff, you can see that the message is being redirected to this netcat server. You might already noticed it, but there is a problem inside our loop. This will continuously run until either one of the clients or the backend closes. We will need a way to tell this load balancer that I am done sending my requests. We can do this by checking the request buffer if it ends with a null terminator. A null terminator is basically a special byte with a value of 0. If you use a low-level language like C, you might be already familiar with this. So we will be checking the request buffer if it ends with null terminator. If it ends with it, we just send the final request -1 to exclude that null terminator. Else just call our normal writeAll function. Before we go any further, let's also address the fact our load balancer is operating in a single thread. If there are two requests that come in, the second one has to wait for the first one to finish, which is not ideal. To solve this, we will be using Tokyo, which is an async runtime for Rust, and we will now be splitting our code better and creating a server we can use for testing. We will first modify our main function to use the Tokyo attribute and remove all of the code inside. The way we will run the load balancer and the server separately is through using command arguments. So we will get the args, and skip the first one since that one is the path to the project's binary. Next, we will be getting the command and pattern match it. We will be creating the load balancer later, but for now, we will create the server. Inside the server check, we will get the host, and port from the arguments, and combine it to make a full address. We will now call the start server function with the address we created. The server that we are going to create are very simple. The server will be accepting a number request, and based on that number, the server will calculate the Fibonacci sequence and return the result. So, we will be doing the usual of creating a TCP listener and start accepting requests. But this time, we will be using Tokyo's module for it. We will spawn a new Tokyo task and call the handle request function. Inside here, we're going to create a vec called request. This is where we're going to store the request the server will receive. And we will also be doing the same thing we did last time in the load balancer, where we loop over and over to get chunks of the request, but this time we will be storing it into the request I just mentioned. Now that we have the request, we will need it to be a number to do a calculation. So we will convert it into a string, then parse it as U64. Then we can do a Fibonacci calculation on it. Our Fibonacci function is very basic and designed to be inefficient. This is to simulate real work where delays and heavy computation is going to happen. And of course, finally, after we have the result, we can reply the result back. We can test the server by running the cargo run with the server at the end of it, along with the address and the port. And in the other terminal, we can just use the printf command and pipe it into netcat that will send a request to our server. Now we will work on our load balancer. We will first go into our main.rs file and call the start load balancer function in our pattern match. And in this function we will, again, do the usual of creating a listener, accepting connections, spawning a Tokyo task, then calling the balance function. Before we go into the balance function, let's talk first about how our load balancer knows which server has the least load on it. For our project, we will keep a local data in our load balancer that tracks the current traffic on it. This data will be a hash map, where the key is the server address, and the value is the current traffic on that server. So we will make a hash map and call it data, but for it to be passed around in Tokyo tasks, we need to wrap it in arc. And to make it mutable, we also need to wrap it in mutex. Inside our loop, we will be cloning the data and passing it into the balance function. Cloning the data here is very cheap and synced across Tokyo task thanks to ARC and mutex, which stands for Atomic Reference Counter and Mutual Exclusion. If you want a deep dive on how it works, or even creating something like it from scratch, let me know down in the comments. In the balance function, we will first get the server that has the least load on it based on the data by calling the getLeastLoad address function. Inside this function, we will just get the data reference. Then we use min-by-key function to find the server with the lowest load. Also in this function, we will be increasing the load by 1 and returning the address. After we get the server with the lowest traffic, we will connect to it. Next, we will be splitting both our client and server stream into read and write halves. This part is so we can have an owned value that we can pass into another Tokyo task. This task will be responsible for redirecting the request to the server, and this one for getting the response back to the client. It's the same thing as before when reading the stream, but here we are using the split halves to read and write. Here we are reading the client request and writing that into the server. Same here, where we are reading the server and sending that into the client. Next, we will need to know if the connection is done, so we will be storing their respective tasks in a variable. Then below, we will be joining both tasks together. After the connection is done, we will be needing to decrement the load in our stored data, so we will get the data reference. Then decrementing the load. And finally, we will be telling our data which servers exist, so back in the start load balancer function, we will get the data reference and insert 8 servers using a loop. And that's pretty much it. Our load balancer is complete. What you see right now is the load balancer we created in live action. We have 8 servers doing Fibonacci calculations simultaneously with 1,000 concurrent connections. And that's it for this video. Thanks for watching until the end, and I will see you next time.